Okay, welcome everyone to my continuation of what is algebraic graph theory. Today I would still like to talk about the Laplacian and about clustering methods. So kind of finish the story I started last time. And there was a mistake last time. I messed that up. We'll see that in a second, in the sense that I was talking about the second largest Laplacian eigenvalue when I actually should have talked about the second smallest Laplacian eigenvalue. There you go. Smallest, largest, very difficult to distinguish, at least for someone like me. Anyway, I hope you will forgive me. And in this video, I'll talk about the second smallest eigenvalue. Anyway, so the video is about partitioning made easy. So let's just get started, I guess. So clustering is a really important thing in everywhere, like data analysis. Think of you have a lot of points somewhere and you want to cluster them into clusters. So I have k clusters. So here k is 2, for example, here k is 3, and I want to kind of break my data into kind of little clusters such that it makes sense. So this is a really nice clustering here that looks very good. This looks very good as well. And kind of the question is, how do we do that? But before we answer the question, we actually won't answer that question. We will turn that question into graph theory, into a graph theoretical question. But anyway, before we can even answer this, let me explain what clustering means. This means you choose k centers. So here we have two centers. Here's the center, and here's the center, such that to minimize the distance for all points. Right, so all points, and you see it very nicely in this video. So kind of for all points, the distance here is minimized to at least one of those centers. And depending on what side, kind of what center they belong to, that's exactly the cluster where they appear. So similarly, here the center might be somewhere around here, might be somewhere around here, or somewhere around here, and you will see that the distance is somehow always minimized. And it's a really, really important question, like data, right? You have a lot of data points, you want to see some patterns, you want to cluster them. And there are actually really good algorithms to do those in R to the M. And I should say here that they are not optimal usually, but they're really good. So like they find the best clustering where everything is really minimized. So the problem here is that you need to minimize literally everything. And that's usually very difficult, but you can do in an heuristic way very, very nicely, like 95% that you get into the correct cluster. So that's really good. So you have really good algorithms to do this in R to the N for any kind of number of centers you want. Like I said again, the problem itself is really difficult somehow because you would need to minimize over all possible choices of centers, which is really, really difficult. But if you kind of cheat a little bit and you're not up for the perfect solution, but for a good enough solution, it's actually not so bad and you can really do it. Okay, so that's the setting. And now we want to do the same for graphs, right? Kind of the same type of question. You can think of now the distance as being like distance in terms of length of paths, and you would like to cluster your graph like in this picture here, right? So you have little clusters and kind of the distance is minimized, and here 1, 2, 3, 4, 5k would be 7 in this picture, right? The same picture, but now not in real space, not with data. Well, graph could also be data. Anyway, so with graphs, right? So you want to cluster graphs. And there's a really funny and extremely good way of doing this, and it works as follows. So let's say we have given our graph and we want to cluster it. So we have a graph. So what do we do with a graph? We compute its eigenvectors, because yeah, that's what we do in spectral graph theory. We compute eigenvalues and eigenvectors. So let the u1 up to um be the eigenvectors. So m is here, will be here my dimension of my space, right? So we have m of them, and we take them for the smallest Laplace eigenvalue. So counting from backwards, that was exactly my mistake. So we're counting backwards now, like the second one will appear in a second. So these are the ones for the smallest Laplace eigenvalues. And then you can assign a vertex in real space to this to those eigenvectors. You can assign quite a few of them, and then you can run the clustering algorithm from before. So we say it again, you run this one here. You compute the eigenvectors for the smallest Laplace eigenvalues. The eigenvectors give you points, and you then run the corresponding cluster algorithm in R to the M. And you can also check that this gives you a good but not optimal solution, for clustering graphs, and clustering graphs in general is really difficult. And here you have a heuristic, which is beautiful. You just send it into R to the M and plays a game in R to the M via eigenvectors, and you just do that, and you get a almost perfect solution, which for most practical purposes, honestly, is good enough anyway, right? So whether you have a solution which is absolutely optimal or whether you have a solution which is essentially optimal doesn't really make any huge difference. Anyway, I say it again. So the trick here from the discrete setting, right? So discrete setting of a graph to the continuous setting of R to the M is to use the eigenvectors to get points in R to the M. And then you can run the cluster algorithm. And the one we have seen last time with the mistake that I should have used the second smallest and not the second biggest eigenvalue, anyway, is the clustering for k equals 2. And the only thing we do is we choose one eigenvector here, so the whole clustering takes place in R1. It's kind of the easiest example of clustering, right? Cutting a graph into two big pieces is clustering the graph for k equals 2, right? So here's my big piece here, and here's my bigger piece here. And the way how this works, kind of the special case, is you just take this eigenvector for the second smallest. You can see it here. It gives me a point. It gives me points in R, and then you run the clustering algorithm. And in R, the clustering algorithm is very simple. You somehow cut wherever the sign changes, right? So that's essentially what's going on here. And yeah, so you can see that this does really, really well. I should say it. It's not optimal in general. It just does really, really well. And that's kind of enough for any practical purposes. Anyway, it's kind of a cool thing. You can kind of really well cut your graph into, in general, more pieces even. And the only thing you need to do is you need to look at some real numbers and optimize a problem in real numbers. But again, here the main players are the eigenvectors and the eigenvalues for the corresponding Laplacian in this case. It's kind of very surprising. Yeah, so, and for example, what you can try to prove with kind of this method, or what is kind of included in clustering, in the theory of clustering, is the following theorem. Suppose we have a graph, G, and we have some subset of vertices, and we are interested in whether the complement graph, so the induced subgraph here, is disconnected. And this happens, so my second smallest eigenvalue is this one here. This can happen only if W is big enough. So the second smallest eigenvalue is therefore sometimes also called algebraic connectivity. Algebraic because we just computed algebraically, and connectivity because, well, the property of finding a subset, right, such that you can disconnect your graph, I have an explicit example in a second, is somehow very tightly tied to the second smallest eigenvalue. And the induced subgraph just means you take, well, a subgraph is anything, but the induced one is you just take the edges, the corresponding edges. If you can take an edge, you take the edge. And yeah, so from the clustering algorithm, essentially, this is saying that this is not perfect. This is not perfect. This is not an equality, but it's a lower bound. And it actually works very well in practice. So let me show you the example. And again, this is just saying how fabulous this idea of using eigenvalues and eigenvectors actually is. All right, so here I have a graph, and my induced subgraph is the red one. And I took out one vertex, and the induced subgraph is clearly connected. So the Peterson graph, that's the name of this graph, has the second smallest eigenvalue Laplacian being 2. So this theorem tells us, let's read the theorem, that I need to take out at least 2 vertices to disconnect it. And yeah, whatever kind of vertex you take out, just one vertex, it won't be disconnected. You need 3, I think, in this case. So 2 is not perfect. But if you just take out 1, you can be sure by the theorem that the remaining part will not be disconnected. And the bigger, maybe that's kind of the point here, the bigger this number is, the more, well, the more vertices you need to take out of your graph. So that's why the number is called the algebraic connectivity. I say it again, that's a bound, so it's not optimal, but that's kind of what we expect in algebraic graph theory anyway. So we get bounds. And it's really, really nice. So you just compute one value and you can somehow already rule out, well, let's say it's 10, then you can already rule out everything up to 9. You can't take out 9 vertices and disconnect the graph. I think that's a pretty cute and nice statement. And this is all related to this idea of clustering, and that those small eigenvalues somehow measure the clustering coefficient of your graph. Anyway, I hope you enjoyed this video, and I also hope to see you next time.